Hi, I'm Jim Heffron. These are my lessons in Calculus 1. So what we're doing today is the homeworks for the section on exponential growth and decay. Sometimes when there are a lot of parts, and these questions have a lot of parts, then I might not do 5 questions, might do sort of 4 or 3 questions. We've seen that already with other homeworks. And the second point here is that with these, I'm gonna see if I can get away with as much as I can, not punching out the calculator, because it's not very enlightening to watch somebody else punch out a calculator, probably do it wrong 3 times. So instead, I'm going to try to get away with just writing down the expression. So let's see how it goes. Okay, let's see here. The very first one is from a prior section, as it always is. It's from section 3.5, number 27. So I got to dig the thing up. Let's see. 3.5 is on implicit differentiation. Trying to keep that fresh in my mind. And then there it says, use implicit differentiation to find the equation of the tangent line to the curve at the given point. And a curve is y times e to the sine of x equals x times cosine x, and the point is 0, 0. So as I said, sometimes these ones are a little big. When they're ones that are a little bigger, I usually do fewer questions. Let's see. So y times e to the sine of x equals x times cosine y at 0, 0. Okay. So of course I have to think of y as a function of x and then take the derivative. So I'm writing y of x times e to the sine of x equals x times cosine of y of x. And I take the derivative of both sides with respect to x. And I see there's a product rule there, another product rule there. I mean, I'm off and running here. Let's see. So product rule says write down the first, take the derivative of the second. The derivative of e to the sine of x is a chain rule. So that's e to the sine of x times the derivative of sine of x is, of course, cosine x. Okay, so that's half of the product rule. I wrote down the first, took the derivative of the second. The other half of the product rule is to write down the second and take the derivative of the first. So complicated. That's the left-hand side. The right-hand side is another product rule, so I'm going to write it on a fresh line here. And I'm looking at write down the first, take the derivative of the second. Cosine of y of x, so derivative of cosine is minus sine, and the derivative of y of x is just dy dx. That's half of the product rule. The other half is to write down the second, take the derivative of the first. I'm not going to bother to write times 1. So it's a complicated expression, and I have to figure out somehow what is dy dx in all this. So I could plug in, I suppose I could plug in zeros for x and zeros for y, and I'll just be left with an expression that has a bunch of numbers and some dy dx's. But I think probably what the back of the book wants me to do, just to make my answer fit the back of the book, is to solve for dy dx. So I'll try that. I'll move everything that has a dy dx in it, how about to the right-hand side? So dy dx. And everything that doesn't have a dy dx in it to the left-hand side. So let's see, does not have a dy dx. So I'm looking at y times e to the sine x times cosine x. And I'm going to have to move this cosine of y over. So minus cosine y. I think I've moved everything that does not have a dy dx in it to the other side of the equation. Everything that does have a dy dx in it, well, I already had minus x times sine of y. And then the other thing is up here, so e to the sine of x, but of course when I move it over, it has a minus sign in front of it, e to the sine of x times dy dx. Okay, and of course you solve for dy dx here by dividing. So dy dx equals, and I just have a big fraction, and it's not beautiful. So I guess y cosine x times e to the sine of x minus cosine of y. And on the bottom is minus x sine y minus e to the sine x. Okay, and of course a person finds the derivative by plugging in 0. Find y prime of 0 by plugging in 0 for x and 0 for y. And I'm doing that because, have you forgotten, all the way back at the top of the question, it says at the point 0, comma 0. So that was given to me in the statement of the question. And then that tells you the slope at 0, and then the last thing you do, of course, is y minus y1 equals slope times x minus x1. y1 is 0, x1 is 0. Okay, and again, I'm going to try to avoid actually plugging in because it's not very enlightening to watch somebody else plug in. Okay, great. So really, this is an excellent exercise. That's a math teacher way of saying it was long and complicated. This is an excellent exercise in all the rules that we learned for taking the derivative. Okay, great. So next up in the list of things to do is the section that we're learning from, section 3.8. It says example 3. So for example 3, we have to cover a topic that we did not see on the slides, but that doesn't, we can see some variant on what we learned on the slides. Fresh in the homework, that's not a problem. So Newton's law of cooling says that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding. And then it says provided the difference is not too large. If we let capital T be the temperature of the object at time t and T sub s be the temperature of the surroundings, then we can formulate Newton's law of cooling this way. So it's an equation that has a derivative in it, so it's a differential equation. So d capital T d little t is k, that's the constant in proportionality, capital T minus capital T sub s. Okay, where k is a constant. So this equation is not quite the same as the one that leads to PERT because it's got these two here. So instead what we do is we set y to be capital T minus T sub s, and then you're just looking at dy dt. Of course, when you take the derivative of this, the constant disappears. So you get dy dt is equal to k times y, and now we're looking at PERT. Okay. So here we go. The example says a box of iced tea, whatever, at 72 degrees Fahrenheit, placed in a refrigerator where the temperature inside the refrigerator is 44 Fahrenheit. And then after some period of time, the tea has cooled to 61 Fahrenheit. It says, so what's the temperature of the tea after another half an hour? Kind of how long does it take for the tea to cool to 50 degrees? So they're asking me to run through a problem here of applying PERT in the context where you're doing the law of cooling. And so you have to set y to be equal to the temperature minus the sort of temperature around it. So in this case, 44 degrees Fahrenheit. Okay, so let's give it a whack here. So I think I'm going to start on a fresh sheet of paper. So let's see. These are big. So let's see. You have the starting temperature is 72. The temperature in the refrigerator, so the ambient temperature, is 44, and it says capital T of 1/2 is, what does it say, 61. Okay? Okay, so we set y to be the capital T, the temperature of the iced tea, minus 44 at time t. Okay, then what we've got, of course, is that y0 is capital T of 0 minus 44. So that's just simply, let's see, what is 72 minus 44, 28. Okay, and we're looking at a PERT situation, so we have that y of t is, it's going to be PERT, capital P, capital P e to the RT. Sorry, I got distracted. So we're looking then at an initial temperature difference of 28, e to the r times, e to the r times, let's see, should I work in minutes or hours? E to the r times, I guess I'm going to work in minutes, 30. And of course we know that y of 30 minutes is 61. Okay, so obviously I'm in a situation here where we've been in before. 61 divided by 28 enables me to figure out r. 61 divided by 28 is e to the rt, e to the r times 30, sorry. I take the natural logarithm of both sides. Ln of 61 over 28 is equal to r times 30. So r is ln of 61 over 28, all divided by 30. Okay? Okay, so again, I'm not going to take out my calculator. Or to finish, a person should take out their calculator, but I'm not going to take out my calculator because watching me punch buttons is not fruitful. But I will answer the question. Part B says, how long does it take for the tea to cool to 50 degrees Fahrenheit? So I'm going to answer that question by saying 50 is 28 times e to the, gosh, I got to write this down. So it's ln of 61 over 28 all over 30 t, and I got to solve that for t. Of course, there's only one variable in that equation, so I can do it. It's just going to take me a minute. Let's see. So what do I get? I get 50 over 28 equals e to that mess, ln of 61 over 28 all over 30 t. Take the natural log of both sides. I've got ln of 50 over 28 equals ln of 61 over 28 all over 30 times t. Almost done. So when I move things over, I end up with 30 times ln of 50 over 28 all over ln of 61 over 28. And again, the rest is a calculator job. I'm not going to punch it out. I will caution, though, that I will sometimes see people try to cancel these somehow. I'm sorry, they don't cancel. Okay, I get, that person is trying to think ahead, but they just simply, you can't cancel the 28s or nothing. So just punch this answer out on a calculator, and that's the best you get. Okay, that was example 3. Next up, I'm going to do 2 questions, 3 and 11. And again, these are big, so I'm using a fresh sheet of paper. Question number 3 is about bacterial growth. You got to focus. Folks, it's really not focusing. It's usually pretty good about focusing. Anyway, I'll read it. It says a culture of bacteria initially contains 50 cells. When introduced into the nutrient broth, introduced into the nutrient broth, the culture grows at a rate proportional to its size. That means PERT is the appropriate formula. After an hour and a half, the population's increased to 975. And it says find the expression for the number of bacteria after T hours. So give the PERT expression. Okay, great. So let's see here if I can get this information down that I need. It says, there we are. It says the initial amount, number 3, the initial amount is 50. And there's a lot of stuff about nutrient broth that that's just talk. So it says after 1.5 hours, the population has increased to 975. So so the population after, I don't want to use capital B. So how about the amount after 1.5 hours? 1.5 is what does it say? 975. 975. And of course we know that that's equal to 50 times e to the r times t, so r times 1.5. And again, I used 50 here because that's the initial population. All right, so this is familiar stuff here. We're just going to solve it by clearing out everything but the e expression on the right hand side and then taking the logarithm. So 975 over 50 equals, here's the e expression, e to the r times 1.5. Take the natural logarithm of both sides, ln of 975 over 50 equals r times 1.5. Divide through by 1.5. ln of 975 over 50 divided by 1.5 equals r. Okay, and then the remaining parts of the question say, part B says find the number of bacteria after 3 hours, and of course if I know what R is, and here it is, I would punch that out on a calculator and get 3 or 4 decimal places, but anyway, if I know what R is, that's easy, you just plug it into the formula. So let's see, we have amount at time t is 50 times e to the, what a mess here, let's see, ln of 975 over 50 all over 1.5 t. And again, if it wasn't, if I wasn't doing this on a video, I'd punch that out on a calculator and get 3 or 4 decimal places. So then it says, again, find the number of bacteria after 3 hours. You're just plugging in t equals 3. Find the rate of growth after 3 hours. Of course, you can easily take the derivative of this expression and plug in t equals 3. And then after how many hours will the population reach 250,000? I'm setting a of t equal to 250,000, at which point the only variable in this equation is t. Okay, so for part D, I'm just worried that this is the only one that would give people trouble. So 250,000 equals 50 e to the ln of 975 over 50 over 1.5 t. Great, divide by 50, so 250,000 divided by 50, and I'm aware that it goes in evenly, is e to the ln of 975 over 50 all over 1.5 t. Take the ln of both sides, ln of 250,000 over 50, and again, I understand that it goes in evenly, but I'm not going to do the calculation, and we take ln of 975 over 50 excuse me, over 1.5 t, and solve for t. Okay, so that was number 3, and then the last one I'm going to do here in this chapter, because each of them is longer, the last one I'm going to do is, I think there's room on this paper actually, now that I think about it. So the last one I'm going to do in this section is number 11. So let's see if the thing will focus on me. There we go. Focused up good. I wonder what that was about. Scientists can determine the age of ancient objects. There we go. The age of ancient objects by method of radiocarbon dating. The bombardment of the upper atmosphere by cosmic rays converts nitrogen into a radioactive isotope of carbon called carbon-14 with a half-life of 57-30 years. Vegetation absorbs carbon dioxide through the atmosphere, and animal life assimilates carbon-14 through food chain. When a plant or animal dies, it stops replacing its carbon, and so the amount of carbon-14 present begins to decrease through radioactive decay. So you have the appropriate amount, you have the sort of ambient amount of carbon-14 when you're living, but when you die, you start having less and less carbon-14 because of radioactive decay. Therefore, the level of radioactivity must also decay exponentially. Discovery revealed a parchment fragment that had about 74% as much carbon-14 as does the plant material on the Earth today. Estimate the age of the parchment. So 74%. So it has decayed through radioactive decay down from 100% of the carbon-14 that it should contain down to 74% of the carbon-14 that it should contain. So let's give it a whack. We clearly need to figure out what R is, and using R, we then figure out what is what point are you at 74%. Okay, so let's see here. Oops, there we go. Let's see, number 11. So I'm figuring out here what's R. Okay, so the half-life is 57. What is 5730? So 1/2 P equals P e to the R times 5730. And at first glance, it appears that this is an equation with two different unknowns, but the p's cancel. So you just get 1/2 equals e to the R times 5730. Take the natural logarithm of both sides. You get ln of 1/2 equals R times 5730. And so ln of 1/2 over 5730 is R. Okay, so we now know what the PERT formula is. The PERT formula is A of t is equal to capital P e to the ln of 1/2 over 5730 times t. And again, you can punch that out on a calculator. You can also notice that the ln of 1/2 is minus ln of 2. Anyway, there are various versions of this formula, but I would probably punch it out on a calculator and get 3 decimal places myself if I wasn't doing it on a video. So now it says 74%. So what's t when the amount left is 74%? So 0.74 t. P equals P e to the ln of 1/2 over 5730 times t. And again, we've seen this a number of times now. It looks like there are two variables in this equation, the t and the p, but the p's cancel, and so you get 0.74 is equal to e to the ln of 1/2 over 5730 times t. So that's an equation with only one variable in it. Take the ln of both sides. ln of 0.74 is ln of 1/2 over 5730 t, and so we end up with 5730 times ln of 0.74 all over ln of 1/2 is t. And that's that's why Hewlett and Packard invented a calculator, because you just punch out the buttons and get a couple of decimal places. Okay, very good. Very good. So these seems to me these problems are a lot of fun, and they have a certain pattern, certain rhythm to them. They often go the same way. Okay, very good.